You're here because of Danny, which is awesome. And my informal introduction is that Danny and I go way back. So we started at Michigan State together as new assistant professors in 2013. And we met because we were in some sort of disorientation meeting that they made us go to, and we sat at the back of the room and we said very smirking things to each other. So we became instant friends. And did a lot. We worked on the PQ class, which you might hear about. We had a big NSF thing where I think we were the first program in the country to work with high school physics teachers to integrate computational practices into their classroom. And we did it through a lens of equitable participation as well. So there we are. Look at those vignettes. We're still writing about it. We have a publication. I maybe keep screwing it up because I want to keep writing with Danny. We submitted something in 2022, just got accepted-ish 2025, so we're like getting there. But it's cool because I get to keep hanging out with Danny and talk to him.
That didn't take long.
Didn't take. Now our publication is in preschool. We can walk and talk. That's perfect. So I enjoy talking with Danny about things. I hope you enjoy hearing from him. But here's my formal spiel. So he is the professor in the Department of Physics and Astronomy and Computational Mathematics, Science, and Engineering, CMSE. You see the confusion. He's the Lappin Phillips Chair of Physics Education and co-directs the Physics Education Research Lab. And he serves as the principal investigator for the Learning Machines Lab and conducts research as part of the newly founded Computational Education Research Lab. If that's not enough, sometimes he goes to Norway, where he works in the Center for Computing and Science Education at the University of Oslo. And as you will see, he's really interested in how tools and science practices impact student learning in physics and computational spaces. And he looks at the design of learning spaces, both sort of in classrooms and online, or in tech that support or inhibit student learning. And with that, I'll turn it over to Danny. Let's give him a round of applause.
Thanks, David. Can you hear me okay? Yeah? Okay, cool. All right, cool. Well, thanks for the introduction, David. Thanks for the visit. I've had a lot of fun meeting with folks. I've got about 700 slides to go through, so we should get started. So I'll start with just introducing myself a little bit more. So I'm a first-generation college student. As David said, I have a bachelor's degree in physics, master's degree in physics, PhD in physics, been in physics education. I've done a lot of different things with that. I was a grocery clerk and a custodian for a while. I worked in a coffee shop for a while. I've been a high school physics teacher in the Atlanta public school system. And I co-direct two labs actually now, so the physics and the computing lab, the LLM or LML lab, absorbing the computing lab. But I also work with the labor organizer for our newly recognized union as of this semester. We're in contract negotiations, and I'm working on setting up the election system, which is phenomenal. And this will come back later, but I've had at least 24 lengthy interactions with law enforcement in my life. But I love science. And I love science for a lot of reasons. I'll give you three. Science can explain natural phenomena in ways that is really interesting to me, whether that's the aurora borealis of Rossi or how stars explode with supernovas. I think they can also satisfy human curiosity. I grew up pretty poor, and so the way that we played outside was with tools. So we dug holes in the ground and stuff and ran water across them. And so looking at stuff like this was common for me as a child, and I was just kind of curious about it. And it turns out people study that, including the lab that I used to work in, where we would look at the transition between laminar and turbulent flow using a Taylor-Coetzel, this counter-rotating cylinders where there's fluid inside of it. And I think it can also benefit society very broadly, whether it's clean drinking water or safe vaccinations or computational tools that allow us to do things, solar panels, or even pedals for sweet licks. And I want to share some axioms with you as well, sort of how we think about this. So I think science is for everyone. I think it can be an immense public good, and it must be representative of everyone. And if you follow those axioms, the implications are that everyone can develop a positive stance towards science, anyone can develop a deep understanding of science, and anyone can shape the work and practice of science. And that's something that our groups really do believe, that talent is everywhere, but opportunity isn't. And so what we try to do is discover, design, and develop the conditions and environments in which all folks who are learning science can thrive. Because we really think that the more folks that learn science better, and the greater diversity across all science, you end up with a science that's more representative of and responsive to society, and you end up with a society that is deeply valuing and strongly supporting science. And these are like mutually enhancing things, right? So if we do this, we get this. Okay, now I'm going to tell you about all the stuff that is not about AI real quick, which will highlight some of the work that David and I did together, just to give you a brief overview in case you have other questions. So one of the big things that we worked on at State was going beyond active learning. So we did a lot of work in three-dimensional learning where we tried to revamp our physics, biology, and chemistry gateway courses for students. This is just a lot of stuff, and you can look at it, but effectively what we did was we went into classrooms and said, well, we're doing active learning, but what are we actually teaching? Right? What are students actually doing out of this? So we took a 3DL approach, which is from the next generation science standards to do that. As David said, I've worked on a lot of course development, mostly community-based courses and non-competitive courses. And so projects and practices in physics, or PQ, is one of our courses. We have a mechanics and E&M version of it for science and engineering majors. It is a group-based course that's taught with computing and focuses on modeling. In addition, we've done some lab work trying to expand the role of investigatory practices in our laboratories, particularly for our students in health sciences, because our students funded that way. As David said, most of my career has been on integrated computing and physics, and I'll show you a little bit of that work. But some of that includes, looking at research. Some of it is working on building faculty professional development communities. Some of it is actually working with my department to integrate computing into our program. And as David alluded to, we've done this also with pre-college physics educators. This is work that David and I and Nero and Paul and a bunch of other folks worked on to take those ideas of computing and bring them into high school spaces with high school teachers and give them the space to design for their students. And lastly, I worked on diversifying graduate physics programs by taking on directly the admissions processes and practices that we engage in, understanding those quantitatively to say, who are they leaving out? And by doing that, Michigan State has changed fundamentally the way that we actually review applications. And so now we have a more holistic review of our applications, and we're getting different applicants. We have one of the most diverse graduate classes of any physics program in the country as a result of this process. But that's not why you're here. It's big brains, huh? Talk a little bit about artificial intelligence. I'm going to start with a disclaimer. My views on AI don't reflect those of Michigan State or any of the organizations with which I am affiliated. So just so you know, these are my ideas, so AI has arrived. We've all been told it's going to disrupt things in education. These are just screenshots from various news articles, including this one, which I find particularly disturbing, where, I don't know, the AI is some sort of presence in the room that's this is a very interesting here. But the idea is that we are being told, right, that this disruption is happening. And there's a lot of things that are being discussed in this space, including potential benefits. Things like personalized learning, or working on enhancing student engagement through different kinds of processes. If you are interested in improving learning analytics, we can do more analysis of student engagement and interactions, expanding access to education, and so on. But there's also a number of concerns that I think are expressed, right? When we think about algorithms have bias. And if we start using them, are we automating things like inequities, right? And does that lead to some dehumanization of education or potentially the deprofessionalization of teaching, right, in job losses? And of course, there's issues with data privacy and security when it comes to using that kind of federally protected data in these systems and using that to make judgments. So there's a lot of concerns, I think, that we should be thinking about. But I want to start by actually defining what artificial intelligence is. And so I'm going to use this model for you. So I think that machine learning is sort of the start of this process, right? It's sort of where we started understanding how we can use data to make inferences. And then we move into what the literature would call weak AI or narrow AI, right? This is the idea that we have tasks that are very clear, with models that are very clear. We have things that we're trying to do that are very, not very simple, but they are complicated, but they are very specific kinds of tasks. And then there's so-called strong AI or AGI, or artificial general intelligence, and then there's so-called artificial superintelligence, which sounds like a sweet name for a band. But when you think about artificial intelligence, it really depends on who you ask what they mean by that. So here's a conversation with Sam Altman. We know how to build AGI. This is from January. And Les Finger says, I'm not so sure about that. But it also depends on when you ask. So this is in August. And now AGI is not really the right term anymore, right? Human level AGI is not a super useful term anymore, right? And so this becomes very confusing, because what do you mean by artificial intelligence at this point, right? Like, what are you talking about? And frankly, we've been here and are there and are likely to be there for quite a while. If you don't believe me, you can certainly look at the different kinds of things that people are advancing, right? You can look at the history of this work. I'm certain that there are people that are working hard on these other issues, but we're still working on these tasks that are relatively narrow. And that's fine. I think that there's value in that. So I would say, forget the hype for a minute, right? Let's focus on what students should know. Let's focus on what they should do, right? That's really critical. And so when I'm talking about AI, this is what I mean. I think of it very broad, and I think there's lots of different classes of it, right? There's statistical machine learning is a part of that. It's a way of understanding data and patterns. Whether it's neural networks or deep learning or any other sort of kin, right? That's part of artificial intelligence. Natural language processing work, part of artificial intelligence. And then, of course, text and transformer models and generative AI, which is, I think, what a lot of folks are talking about when they say AI. So I want to frame that issue for you just a little bit. You don't have to believe me, but these are just ways that help me think about what we're trying to do. And I would say no single frame is actually relevant in all contexts. I also think they all have value. So if you take the approach of technological solutionism, you might consider that the AI is providing necessary solutions. It's helping us scale. It's helping us do efficiencies. It's helping us emphasize personalization and so on. You hear this from folks that I've named here: Salcon, Michelle Reed, Daphne Kohler, Sam Altman. Right? You're technologists. You're people who are invested in the technology. I think another way to frame it is to think about human-centered education, which is, I think, a lot of what we tend to do, especially in disability-based education, which is think about the humans in the space. And social relationships there are quite important. We're emphasizing critical thinking, right? We're leveraging experience and experiential learning. And we're promoting something bigger than just content understanding, socio-emotional development and metacognition and so on. And the folks that sort of, I would say, fit into kind of that band are your John Dewey's, your Seymour Pappert's, your Andrews, Sessa, and so on. And the last frame I want to present to you is education as a tool for justice, where we think of education and knowledge as a tool of black liberation, where here we're promoting diversity and equity, social justice, and we recognize that our educational systems are inherently inequitable. And these are folks like Paulo Freire, Bell Hooks, and so on. So if you take these frames, these are maybe active at different times. And then we kind of layer on the rapid development of Gen AI. Right? So when we look at this rapid development of Gen AI, I think we might suggest, or I might suggest, and I have, that the development here is too rapid for research to keep pace. When you look at the ways in which this stuff is developed, it developed on the timeline of months, right? And even in some places, weeks. And if you look at the work that's been done in science education, which my colleagues work in, the timescales for shifts between ideas in science education is decadal. It takes about a decade or more for a new idea to come into the field and be used. And so this scale here is in months, and this is in decades. There's a mismatch here, right? Don't worry. There's been little gain, so we're okay, right? Despite the billions of dollars in capital investments, it's not the good that we've necessarily been promised. So here at tinyurl.com/McKinsey-AI-BS, you can find a McKinsey report on AI and how they advance the idea that workers want AI. Your managers need to get on board with doing AI stuff. And here's a graph that they show indicating, there are 4% of the C-suite and 13% of the employees, and that's 3, I'm not sure. I'll tell you more about that. But if you actually look later on, where people are starting to do studies of this, so this stuff happens that came out in the summer, you find that you don't get those kinds of benefits that they may be arguing for. So these are two studies that came out of the MIT Media Lab, and you probably have seen some of them. The first one is like an fMRI kind of study where they gave students the opportunity to use LLMs in their coursework and not. And then they looked at brain activity. Now, you can have whatever view you want about brain activity, but it's an argument that they're saying certain parts of the brain are inactive or not as active when people are using LLMs. That's interesting. If you want more study, different kinds of studies potentially. The other one is when AI tools and agents have been implemented in business, only about 5% of them actually remain. If I tell my kids, if you do your chores, you got a 1 in 20 chance and you pay me for them, you think they're going to take me up on that deal? I would suspect not, right? And so we want to think about how we're investing these, investing in these tools and how they're being used. Because what we're seeing here is a 95% drop-off in these investments, right? People are putting money, energy, personnel towards these things, and they're not being invested. There's not much benefit, at least right now. Now, I want you to also witness the genius of AI. So I asked an AI system, how many R's are in strawberry? And it told me one. And I was like, are you sure? And it's like, no, 2. And I was like, are you sure? No, 3. Are you sure? No, 4. There's definitely 4, right? So what I'm trying to get across with this is that communication with somebody with knowledge and prompting an AI system, those are different things, right? Having a conversation with that system. Now, fair enough, this is an open weight model running on my laptop with only 3 billion parameters, right? It's not the 400 billion parameter model that may do this a little better. Also, bigger and more advanced models perform better because there's a lot of baked-in programming to make that happen. But the point is that all of these models generate mistakes, right? And how are learners supposed to know that that's a mistake, right? There may be some things that are obvious, like this, right? But there's probably things that are less obvious, especially when you're learning coding, physics, biology, whatever it might be. All right, let's talk about energy and water. So when you look at the training of these models, OpenAI is quoted as having used 50 gigawatt hours to train GPT-4. That's the amount of energy that's used by 1.6 million homes in a day. It's a lot of energy, right? Inference is when you are actually interacting with the system and asking it stuff. And it turns out that that uses about the energy that your microwave uses in a second, typically. But ChatGPT is the 5th most visited website in the world. And it has 2.5 billion prompts per day. So every day, about 1 gigawatt hour of energy is being used on inference, just for the OpenAI system, right? There's many other such systems and so on. So there's a lot of energy that's being used. And moreover, I don't know if y'all have seen these Sora videos. Folks seen these Sora videos? So these are the videos that are artificially generated, right? Those take 285 times as much energy to generate 5 seconds of video. Very expensive. Lots of energy being in that work. Let's talk about cooling. Okay. Millions of gallons of water are used to cool these data centers daily. So much so that local cities, right, are trying to inquire how much water is being used by these companies, and it's being obscured. There's a very good case study of this in the Dalles, Oregon. It was Google that started a data center there, and the citizens sued Google and their city to figure out how much water Google was using, because then Google got into the contract with the city. Part of the contract was we're not going to disclose how much water we're using. So your queries consume about 8 to 16 ounces of water, right? And the expectation, this is coming from, I think, one of these energy things, AI is expected to use about 22% of all U.S. energy in about 3 years. That's a lot. So I think one of the things we got to think about is what are we teaching, who benefits, right? And what futures are we actually enabling when we do this? So I'm going to tell you about the state of Michigan. Maybe some of y'all are from Michigan. So here's the state, the 2 peninsulas. They're pretty sweet. All the major cities are in the Lower Peninsula. There's about 10 million people in our state. Most of them live sort of down here between sort of Detroit, Lansing, and Grand Rapids, kind of that thoroughfare. Very much like you all, right along I-15. Yeah, very similar. Right? Very large amount of population along this route. Most of our industries involve manufacturing and automobiles, as well as food and fresh water. We touch 20% of the world's fresh water, very important to us, very, very important to all of us for this to be taken care of. And then our fifth industry, Christmas trees. So I think there's like 4 industries for which AI is probably relevant. I don't know if Christmas trees necessarily have a need for AI, but maybe. Those are all in the Upper Peninsula, by the way. Michigan State's a big school. It's a little bigger than this place. So I live in a city with about 47,000 permanent residents, but 52,000 students. It is a college town. There's about 5,000 academic staff, including 2,000 of us that are in the tenure system. We're a land-grant university. We're the lead land-grant university in the state of Michigan. We're responsible for public education and the public economy. We were historically an agricultural school, but we have a lot of things going on. STEM in Michigan is I'm just going to share this with you because I don't know what STEM is like in Utah. But STEM in Michigan is interesting. It's an interesting place, and it's a challenging place, I think, because a lot of our students that are in our K-12 systems aren't necessarily achieving the proficiency in math and science. They're not achieving the college readiness that we might expect. Now, we can dispute sort of the measures and so forth, of course, but I also think that this is something that we should be thinking about if we're thinking about preparing students for science. That there's some sense here that we need to do that. Advanced STEM courses are not accessible to many of our students, mostly in sort of Detroit and Grand Rapids and Lawrence area, although it's not really prevalent. And of course, students of color and those who are economically disadvantaged are further disadvantaged in our state. The other thing I think that we need to remember is all these systems are interconnected, right? So when students start in K-5 and go to university and then go off and do their STEM work, they come back into these places as well, right? And so I think one of the things that David and I work on and appreciated is that there is this connection, right? That you have to do this kind of work across the system to understand how it's all done together. So I think a new challenge lies ahead of us because there's different forms of AI in many different spaces, whether that's in research, in data analysis, modeling, control systems, translation, so on and so on, and including a bunch of places that we don't know where it will be used, right? And that's going to require some nimbleness on our part to pay attention to that and then act, right? So I think one of the things I want to really make sure that I emphasize here is when you're talking to folks about AI, make sure you talk about the same kind of AI, right? It's not just Gen AI. AI has done a lot for us in science. I don't have time to show you sort of all the advances in like physics-informed machine learning or how we use neural networks to do this kind of work, but it's really advancing what we do in science, right? Not necessarily Gen AI, but these other forms of artificial intelligence that I'm telling you about. Okay, so I'm going to tell you some stories about state and frame this with sort of some frame our active efforts here, right? So I'm going to start by talking about teaching and learning about AI. I'm going to give you some examples from our department in computational math, science, and engineering, which I hope confuses you greatly, since our acronym is CMSE. Good luck with that one. I'm going to talk to you a little bit about teaching and learning with generative AI specifically, and then we'll talk a little bit about teaching and learning against AI, and I'll motivate that. And this is, my colleague Aman Yadav actually has a really good framework for this that I am stealing from and misremembering, and apologies. So let's talk about teaching and learning about AI, and focus on the undergraduate programs in data science. So my department, one of my departments is computational math, science, and engineering. We are a department that sort of sits at the nexus of computer science, disciplinary modeling, and mathematical approximation theory. So my department is half applied mathematicians and half scientists that do computing in some spaces. That could be electrical engineers, it could be computational astrophysicists, it could be biologists, we have plant biologists, and neuroscientists, and so on. But our focus here, right, is not computer science. Computer science is the science of computing. We're focused on the computing that does the science. That's what we're very interested in, and those are the kinds of, that's the kind of training that we provide, and that's the kind of degree program that we have. We have a bachelor's program, a master's, and a PhD program. I'm going to talk to you about the bachelor's program mostly. So we teach computational data science. That means a lot of things. It means that we teach students about ethics, which I'll tell you about in a minute. It means we teach them about visualizations. We teach them about modeling data. We teach them about using Jupyter notebooks for communication. This is like a clustering algorithm. I don't know where that came from. But all these things are taught in these classrooms where students are working in groups, and I'll show you a little bit more of that in a second. Our BS in data science, these are the degree goals for the degree. Solving real world problems using data science techniques, obviously that's important to us. Engaging in critical thinking and designing those, in the design of those data science techniques. Communicating and collaborating about your ideas in data science. And most recently, understanding the human and ethical implications of data science and integrating that knowledge into your work. This is a new departmental goal for us. This is a new degree goal for us. So I'm going to show you a little bit about that. The core coursework, and there's a lot of other stuff that they take, but they take some intro computational modeling courses, some probability courses. I'll tell you a little bit about fundamentals of data science methods, and then obviously some additional courses in machine learning and big data analysis. This program partners pretty strongly with CSE, which is Computer Science and Engineering. It's our CS department. So the CSE courses are offered by them. There is also a computational data science major in the CS program, which is basically our major. There's more CS and less CSE. So there are students that are taking these courses in both programs. In our Intro to Computational Modeling, this is a CMSE 201. This is a flipped course, and it's taught in a 50 to 70 student section where they're working in groups of about 6 or so. This is an introductory course. It only requires Calculus 1. Other than that, no coding experience necessary, just Calculus 1. So we teach students how to engage with data science through the use of these Jupyter notebooks. I'll show you an example in a sec. But mostly what they're doing is working together to figure out how to model the problem that they're engaged with that particular day. So here's a brief snapshot of the way that we do this progression. So we start with sort of order of magnitude estimates, we move into physical systems, we talk a little bit about evaluating the states and so forth, we get into visualizing and manipulating visual data, and then we get into modeling with different kinds of progression models, we get into ethics later, et cetera, et cetera. There's a bunch of different things here. The important part here is really the programming practices and tools that we're introducing in these cases, right? So we're teaching students how to use the Python environment and Jupyter environment to do their analysis. So that includes like defining variables because they have never computed a thing before, right? That is not a thing they assume. So we're starting from doing simple math all the way to loading files and making plots and then eventually doing regression models and solving lineages and so forth. This is what the class looks like. So this is an old picture. It's a little bit of the new room. But you can see here that all the students are sitting there with laptops, so they're all writing their own code at the same time. They are discussing it. They can plug in and show each other work. This is my colleague, Mike Morello. He's just, talking to folks, seeing what they're up to. A lot of it is just kind of going around and seeing how students are doing and making sure that they're talking with each other about their activities. So I'm going to show you an example from the follow-on course. So CMSE 202 is what students would take immediately after. And so in this course, they are really starting to figure out how machine learning works and how to do that modeling process. And so here, what they're doing is they're looking at a correlation matrix. They're applying a heat map, really here to show what features they want to include in a regression. That's their task for today. And so they go through, they produce this, and then they're asked questions of, well, how are you going to pick your features? Why are you going to pick those features based on your correlation plot? And so they describe that. And then they produce an analysis, right, which produces a report. So they model this with stats models or whatever, and they then answer, how does this fit compared to the full model? And the student gives an answer that is focused mostly on the R squared, just R squared. This is real data, I'm showing you what students say. But the idea is that they do a programming task and then they engage in some form of sense making. What we've added to this now, not just this programming, is engaging more with ethical decisions. So in CMSE 201, just jumping back for a sec, we engage students with issues of bias, right? And how algorithms can develop bias, how they can be inherently biased, and then how that can apply to real-world outcomes. So in this case, if you haven't, you should pull this up. You can just Google survival of the best fit. It's a game on the web. And you can play this game. The point of this game is for you to figure out who to hire. You're given this piece of information and that piece of information. You hire blue or orange. And you pick each person. And then what it does is it brushes you. And it brushes you and it rushes you to make decisions faster and faster. And then it builds a model based on your decisions, and then it algorithmically applies them. And when it does that, it shows you how biased you are in your approach. Right? And so this leads us to have a conversation with students about the lack of information in making these kinds of decisions. What does it mean to sort of outsource the decision-making of hiring to a model? How do you understand the bias that would come out of that situation? And so through this discussion, we're actually really trying to engage our students in a critical understanding of the choices that we make when we use algorithms in our approaches to really, I would say, sophisticated things. Hiring people is a sophisticated thing. Shifting gears just a little bit, this is one of our major courses. So this would be after they've taken 201 and 202, they've taken Fundamentals of Data Science Methods. This is really a full course in machine learning analysis, modeling, and evaluation. And what's interesting about this course to me is that it's taught by scientists who do this for a living, and they bring in things that are really important for people to consider when you're doing this kind of work. So they're teaching the students here about crossroads validation, right? Just how do you validate a model when you have samples that you're drawing from, how do you understand that? And as they're building that understanding, they're then also presented with a real-world example from schizophrenia research, which shows you that in different approaches to validation and modeling, you change the accuracy of different features, which suggests that you have a strong sort of context dependence to the way that you are making conclusions about the effectiveness of schizophrenia medication, but also that predicting the impact of that medication is very, very different. Right? And so that conversation with students is really important because it says, well, you can model this, sure, but the implications of that modeling are really important to consider, especially when people's lives are on the line. I put this slide in the wrong place. We're going to skip that and we'll come back to it. Okay, I'm going to shift gears here for a second and talk about teaching and learning with Gen AI. And I'm going to give you an example from classical mechanics, and then I'm going to go back to a slide. So I teach classical mechanics, which is our sophomore, junior level course in physics. These students basically are studying the motion of systems where the calculus that they have to do is more sophisticated, and eventually where it has a different formulation of mechanics, which for the physicists, right, we get to Lagrange dynamics, basically. In that course, we use computational essays as a form of assessment. So students are meant to learn the practices and processes of classical mechanics and apply those to new ideas. So I'll show you some examples of that. And I would say as a result of that, as a result of pushing them to do this kind of creative work, they do use generative AI in my class to do some of these things, pushing them a little bit beyond where we are in class. So this is the class. It's in this beautiful room here, which is kind of like this room, just to pick over a little bit. My students work in groups. We do a lot of clicker questions. This is not really relevant for anybody really, but this is just a way of them understanding how the systems work and so on. What I really want to highlight is the midterms, where students are using generative AI to develop models of systems often. So here's the midterm, actually the midterm they turned in last Friday. So they're given a potential for some sort of one-dimensional system. They're asked to go through the canonical steps that we would go through to analyze that system, including numerically modeling it. And then in the next problem, they have to choose their own one-dimensional system with particular parameters and then do a similar kind of investigation. And what I find is that students are able to sort of transfer this process with this idea, but then are often using generative AI to check some of the code, right? To check some of the analysis that they've done, just a little bit. As we get farther along, they definitely use it more for generating code. So this is the second midterm, which they haven't gotten yet, and they are asked to basically investigate the Lorentz retractor, which is a canonical system for us. So they build a numerical model and logics, et cetera. And then they're asked to decide how to illustrate chaos or chaotic dynamics or what have you with a particular kind of system. And they make that choice. And so this is a diagram showing you what a student actually did. So in this system, they modeled a cluster of points, and then they allowed it to evolve in time. The yellow points are where everything happens, right? And through this, they're sort of showing the sensitivity to initial conditions, how they distribute themselves on the attractor, and they make arguments about sort of how it's showing dynamics, right? The dynamics. The student who did this work, they came up with this idea on their own. The challenge they had was how to distribute the points, those pink points, right? And so in class, they were working with generative AI to figure out, how do I kind of place a cluster of random points in this space so that I can keep track of it and calculate sort of all of these points as I go along? How do I do that efficiently, right? And they were able to do that by taking their code and making the initial conditions a vector and handling it appropriately, right? And that's something I did not teach them how to do, but it was something that they were able to do, like by tracking one point, okay, I can figure out how generative AI is telling me to do this for lots of points. This is all part of a long-term effect. I don't have to go through this, but let's talk about AI in the class, right? And so the way that I handle this in my class is I co-develop a policy with my students. So all the things that I showed you, like this stuff, we go through this. I spend an entire class period going through both positive and negative issues with artificial intelligence because I think it's important for the students to develop their own personal relationship with it by considering these different things. And so what we do is we go through sort of these different ideas for the class period, and they work on writing a policy. They create a policy, or a set of policies that they think are going to be useful. Right? They advance those policies in class. We prepare them in proposal form, and then the students vote on them in a ranked choice voting system. And this is the one that they chose. And so this is the students' idea of how they should use AI in their class. They should adopt a policy where they're using it for brainstorming, alpha editing, but it's not for never-act answers. It's not for the completion of assignments. They should document its use, but it can be informal, and the repercussions for not using it are pretty minimal at first. Right? And the idea is to give them some space to make mistakes, to have that conversation, but also to recognize that this is the way that they feel comfortable using it. Now, I should say that not all my students use AI at all. Right? This is just the sort of minimum criteria. There are some students that can go at this entirely and do not engage with it. Okay, I put this. Another approach that you may have heard. So this is just me developing a policy, and then we engage with this in class and we discuss it. Right? That's a thing that I can do because my class is small. There are other approaches. I'll put this slide in. Oh, sorry, I bumped it in. Okay. The so-called retrieval augmented generative AI. You all heard of this? These so-called RAG models? Okay, so RAG models, I see yeses and I see some no's. So RAG models are very, very interesting because think of ChatGPT knowing what you know. That's the promise, right? Is that there's some documents that you can put into the system in some way that allows it to draw on those documents when it's responding to a query, right? And you can do this with ChatGPT. It's just not very good because it doesn't structure your data. Structured data is super important for this kind of system. So if you are really wanting to use this, you're baking in some real structure. This is a hint. This is a direction. This is a solution, right? And building a structure to tell the system, in some sense, what to draw from when it's responding to a query. My colleague, Walter Freeman at Syracuse, is working on building an open source model, open source RAG model. We're going to be piloting it in class because it will allow us to actually see the nature of the structured data, how it's actually coming into student queries, and what students then do with that. This is something you can't do with the commercial systems. You can't see what it's pulling, why it's pulling that, and so on. And so we're really trying to investigate the utility of these by unpacking the back end. Now, on the front end, we're using a system called HiTA. If you're interested in HiTA.ai, it is a RAG model system. It's a commercialized system. It's under the Colorado School of Mines. It can do a lot of these things, but you have to get in touch with them to make sure that you're doing it. You can see the back end of it as well. You can see what it's pulling. It can, et cetera. It can do all these things, but it does cost money. At the moment, we are piloting it for free because we're giving them feedback on the system. But, anyway. All right. Perfect. All right. So the last thing I want to talk about is teaching and learning against it. And here I'm going to talk a little bit about general education in AI. And I'm going to motivate this why should we talk about it as against. I think some forms of AI are very, very harmful. And I don't think that we often acknowledge how harmful it can be. So if you're not aware, this is a program called ShotSpotter or Shotter, I don't know which one. I think ShotSpotter. So what you do is you set up a bunch of microphones throughout a city, and those microphones listen constantly. And they try to triangulate a gunshot, right? And by triangulating that gunshot, they then report directly to the police. There's a gunshot, we think it's here, they send police. Now, there's a few things about that. One, it over-polices places that are noisy, because there's a lot of false positives, it turns out. There's a lot of things that sound like gunshots. And moreover, it over-polices places that have mostly black and brown folks. That's just how it is. And so it's expensive, right? It relies on a technology that's faulty, and it over-polices people that are already over-policed. And so, you know, in Columbus, right? They got rid of it, it was too expensive, it wasn't right. Right? And so I think we need to think not just about like its positive use cases, we also need to think about cases we don't want to be using, right? Or that we would want to advance in ways that, you know, we think are problematic. And the reason I think we really want to think about that Michigan State is because we are the leading STEM institution in the state of Michigan. 75% of MSU students are Michiganders, which is the name for people from Michigan, in case you didn't know. 65% of those folks remain in the state after graduation, right? So the vast majority of our graduates are staying interstate and staying interstate. We graduate the most STEM students in the state. We graduate the most future teachers in the state, right? And we have one of the leading STEM education research communities across the U.S., right? With both Science Ed and DEVA. And so we really should be a voice that's defining what we call AI literacy in some way, right? Because we also have the strength of our K-16 programs, our policy programs, and the research center. And so the problem that we have in front of us when we're thinking about this broadly is that, you know, all students should have this opportunity to develop a conceptual and critical understanding of AI, but we have to acknowledge that it's a complex set of technologies, right? It's not just one thing. And it's being used in lots of different sectors, right? And moreover, the development and its history are actually pretty complicated stories. And programs are rushing to meet a need that they're inferring because there's a fear that if we don't produce something, someone else will, right? That's concerning. I think what we need to do is slow down a little bit and be deliberate about what we do, be intentional about what we do, because the complexity of what we're discussing is actually pretty challenging, right? There's a lot of people who know a lot about AI in different domains that we should be talking to when we're developing these things. When we talk about a holistic understanding of AI literacy, it requires us to talk to educators and historians and sociologists and philosophers and scientists and computer scientists and so on, right? And so if we're thinking about this as like this is where we're going, right? Artificial intelligence is here and it's going to continue to be here. We have to think about both how we sustain our educational systems and moreover, how we adapt continuously because this thing is advancing so quickly, as I showed you earlier. Right? And so what we proposed was two different kinds of courses. One was a general science requirement, so this would be consistent with our sort of science and society style courses that we offer to all students, right? So they satisfy like a science requirement kind of in general. Or for nat sci students, for College of Science students, we offer a course that may be more focused, right? Maybe allows us to do a little bit more programming, maybe allows us to dig into a little bit more science, et cetera. You know, college is not clear on what they want. We're planning this one. So that takes some practice, right? It takes some work to develop this. So we're calling this CMSC 101, and we're starting the process of talking to people about what it should look like, right? Who would be taking it? What might they need? You know, who else should we be talking to when this is happening, right? Whose majors are interested in this, and what considerations should we have? And you can see here there's a sort of phase to roll out, right? Developing the pedagogy. We have a lot of activities already, but we can develop some more. Offering it to a representative group, right? We're hoping to pilot this with 40 students next fall, and then 40 students in the next spring, and then start designing for large enrollment with the goal of enrolling 350 students in a section for this course in a few years, right? And offer multiple sections. The way this course is organized or thought of right now, and this is through negotiation among the college, is that we're going to focus on data, tools, practices, and actions. These are the things that sort of underlie what we do with AI, machine learning, and so on. That there's raw information that goes into those systems, that there's a choice of software or algorithms, that there's things that you actually do as a practicing, you know, AI researcher, that those things are important, and then what you choose to do with that information afterwards. And we've talked a lot to our integrated studies program who does a lot of this work, so we're trying to define what we call AI literacy, at least in context. And we think that that means data literacy, quantitative literacy, and ethical literacy in this context of artificial intelligence, so that we are looking at the data that's collected, who collects it, for what purposes, that we're investigating the analyses and evaluating the quality of the claims, and then we're also examining the societal, moral, and political implications of what we're doing, right? That's a science and society course that we might offer. And so the way to think about it is to look at it like this. Here's a framework that we're working with, right? On the left-hand side is a circle of the sort of data tools and practices piece, right? And that's kind of the process of engaging in AI and machine learning stuff. You can see some questions here, right? What information is collected, what algorithms are being used, you know, in what ways are we doing this, in what ways are we constraining or scrutinizing or critiquing what we're doing, right? Kind of going through that cycle produces some result that you then take an action based on, right? Whether that's a decision that you're making, an experiment that you're doing, or hiring a decision, for example. And through this sort of process, we are trying to go through then 3 steps, right? So where we've been, where are we now, and where are we going? And the idea is that where are we now can continue to adapt, and where are we going can continue to adapt as we see changes happen. Now, I don't expect you to read all of this. But in talking with our integrated studies folks, they were asking, okay, what's the overlap between the way we think about this and the way you think about this? And so we built this sort of overlapping matrix, which shows you, and I highlighted some in yellow for you to pay attention to, because these things are interesting. Right, goals that we would have that overlap here. Right, so for example, critiquing the assumptions of embedded in data processing algorithms sort of overlap between data and tools, whereas critiquing who benefits and who's harmed by AI practices is a practices overlap with ethical literacy. Right? And so having these kinds of goals that are structured within this helps us say, okay, this is what we were saying is AI literacy. It's being able to do these kinds of things. Again, something I don't expect you to read. There's 15 weeks of this course as planned. The topics on the left, the framing is in the middle, the exposing yields is in the middle here, and case studies that we plan. And the idea is to design this course around case studies because those can be moved in and out. Right? As we see new techniques or new approaches coming in, we can bring in a new case that satisfies that idea that semester. And so just to sort of show you the chunks, right? Introducing AI overlaps with this historical perspective, both sort of going into the hype cycle and the Cold War origins of this, but then getting into specifically what data is being used, what tools are being used, what practices are used, what actions are used, to dive deeply into each of those components before we then look at lots of different forms of AI in different areas, whether that's the environment, healthcare, law enforcement, and so on. And again, these on the left here can also be swapped out. There may be other ones that are interesting that develop, as over time. There may be ones that we need to double up on because they become very important. And lastly, evaluating. Right? So the last bit of it is now you have this understanding of the framework. Let's now look at how do we advance it, how do we grow it, right? And moreover, how do we constrain it? How should we regulate it, right? With the final evaluation being that students would design and evaluate a use case of AI on their own using this framework to understand what, in their view, is an ethical use of AI to solve a problem that they think is important. So maybe we'll do this in 12.6. I'll say, so in doing a lot of this work, one of the things that I noticed is that there's a lot of challenges. And those challenges I don't think are unique to us, so I just want to share them with you because I want you to be aware of it. There's no definition of AI literacy. That is something that you would have to come up with, I think, based on your context and what you're trying to do, right? There's copious amounts of FOMO, right? It's just all over the place. And there's a lot of demand for us to do something quickly. I'm not sure what the pressure is, but there's a lot of demand for that. And I think this actually leads to having bad actors and bad behavior, because I think people see this as an opportunity to do something else that is not for the students. And that is something that you may have to deal with, right, as you're thinking about this. And moreover, you may end up with poorly considered partnerships. Our department does not work well with the CSE department, but we're both engineering departments. And so when we talk about AI, turns out we both maybe have a claim to that. And so why shouldn't we work together on this, is what the dean said. I have a lot of reasons why. I won't share them in public, but they involve things like territorial disputes and bad behavior, right? And so these are things that happen, right? Administration making decisions about how to coordinate things. And I think you really need to do what you think is important, right? What we've decided to do is to agitate with action. And by doing that, what I mean is we keep going to meetings with new ideas and just keep pushing them. Here's work that we're doing. Here's actual activity that we're doing. Right? Showing somebody this. We have a plan. People don't often have plans, right? But it's not that we're going to necessarily teach this class, but we're agitating people into having a real conversation about what they want to do in the classroom. Okay, final takeaways. I think it's very important for us to engage with AI and science education. It's going to require an authentic collective effort and precision in our work. I think how we define it and what we're planning to do is really critical. It's essential that we design for AI in science classrooms because the future of scientific discovery is built on advances in AI, I mean, broadly speaking. And it's necessary that students develop a critical understanding of it because we can't let AI be only foisted upon us by billionaires and corporations. They have motivations that are not our own necessarily, and we need to be, I think, concerned about spending students' money, spending institutional money, energy, water, and so on. But I think it's going to be a lot of fun to do. And if there's one thing to leave you with, it's that generative AI is one form of AI, but it's probably the least useful or most wasteful form of it right now. Thanks, y'all.
Thanks, Danny. Always interesting and exciting. We have time for a couple questions, so if you have one, put your hand up and I'm going to bring you the mic. Don't be shy if we bring you the mic when you want to ask a question. This is sort of over here. Awesome. Thanks.
Thanks for that presentation. That was really interesting. I'm also interested in this intersection between K-12 science education and AI. One of the questions I had was related to the sense of urgency that we hear a lot from teachers. So teachers are in a bit of a panic because they aren't sure how to adapt what they've been doing for assessment to be able to recognize the fact that students have access to ChatGPT on their phone, how do you address the urgency of what teachers are seeing like right here, right now, with this idea that we also need to slow so that we understand the landscape a little bit better?
That's a great question and very difficult because I don't. There's a lot of local factors when it comes to this kind of thing, right? And so prescribing a particular approach would rely on me understanding, kind of that whole of it, right? And so I can tell you what we do at state, but I can't tell you what to do at other school. And so the example of mitigating solution. Two of my sisters are third grade teachers in Texas. And their district adopted an AI system for lesson planning. My sisters have been teachers for a decade. They know how to plan lessons for third grade kids. But they have to check in with the system once a week. They have to submit or interact with it once a week, right? And they're checked up on if they don't interact with that system once a week. That's interesting to me, right? Because it means that there was some money that was spent on that system, and there's an expectation that my sisters who have expertise in this should still use that system. That seems problematic, right? And it seems problematic from the administrative side, because it's being foisted upon teachers and so on. On the student side of it, right, they have sort of organic access to these tools. And it's really challenging, I think, especially if your assessments are the typical standard assessment that you give to students, right? Task, multiple choice, et cetera. And so I think it's an open question, right, as to how you would develop assessments that are appropriate for students in that context. But I do think, we have a lot of different ways that we're doing it at state. And I showed you a couple of examples, but like another example that I didn't show you was in our computational science class, we restrict students from using it for the first 7 class periods. Like we asked them not to use it at all because we wanted to understand the format and syntax of the Python code they're writing, so when they get something from that system, they can read it, right? Because if they get something from that that's object-oriented, we don't teach object-oriented coding in this class. It's useful, it can be widely used, but it's not what we do, right? So when you get that code and you copy and paste it and it runs, great. But if you don't understand what it's doing, that's a problem. And so I think in part, right, it's trying to figure out those kinds of mechanisms locally. Like how would you decide? And I don't think there's one solution. I think it really matters the context. And so I wish I had an answer for you.
Thanks for the talk. Do you think with AI and how students use AI for answering their own questions, whether interactions in the classroom can be preserved? Because before AI, it's like if you have a doubt, you probably ask the professor what questions you have.
Yeah.
Whereas now, I feel like interactions have reduced in the classes that I attend.
So your sense is that the interactions with the students and the instructor have gone down
Have gone down,
because the
so
students are using.
other ways
Mhm.
point of view where we can maintain it
Yeah.
in the classroom.
I mean, I guess that hasn't necessarily been my own observation. It might be the case. I think there is a role for this tool, right? I mean, it's an on-demand tool, right? And if it's designed correctly, again, we'll test this kind of open source track model and see how it actually works, right? So that we can teach students potentially how to use it well, right? Because I do think there's value in them, going to something that I trust, right, for my class and say, like, yeah, you can go ahead and interact with that. I know that it's going to do something that's reasonable, right, at least because we programmed it or it's constraints are like that. But I don't see it as replaceable for the social interaction, right, because the learning is situated in the course and it's social amongst all of us. And so I think I see it as like a thing that I would advance, use when you can, but it's not a replacement for me or the team. But I haven't seen the same kind of dip that you're observing.
All right, we already got the last question. Hold in.
Thanks, Danny. That was a great talk.
Mark?
So you talked a lot about the way that you're integrating these ideas in courses that are specifically designed to teach these things. Your gen ed class that you just mentioned at the end, and then your CMSC classes. You've done a lot of work over the years on integrating computation into other, like, to enable other instructors who aren't teaching these things specifically to integrate computation. I'm wondering what you think about this in the context of AI and machine learning. Like the classes that are in physics or some other discipline that aren't specifically about this. What are your thoughts on integrating ethical implications? Some of these ideas, but in a different class, discovering different subjects.
Yeah. So just to say back to you what I think I heard you say, Jordan. So we've integrated, we're working on integrating these ethical components into the data science major as a major. And then what I'm hearing your question is, well, that's great, but what about another degree program, like physics, for example? And ethics is not a learning goal in our program. I mean, it should be, right? But it's not a learning goal in our overall program. Right? So our students, the physics students, would experience that if they took CMSC 201, which they have to because our major requires it, and if they took 202, which many of them do because they're interested in it. So I think their only real exposure to it would be in those spaces. I could imagine us having an ethics expectation when it comes to our degree program, which goes beyond generative AI, right? It's about doing research and collecting data and being true to your experiment, et cetera, right? Those kinds of things are also important, which we're also not doing. Thanks for giving me more work.
Yeah, so the philosophers, I hang out with philosophers sometimes, and they would love for us to talk to them. So, we ask these, we've been asking these questions for 1,000 years, so I'm hanging out with this. We are a little bit over time, so let's give Danny a round of applause.